So much about measurement-based quantum computation, and now we need to talk about the other half of the story, about contextuality in quantum mechanics. Okay, let me summarize what this means, or what the result is, and we go into the details of that. Non-contextual hidden variable models contradict quantum mechanics. The two don't fit together. So that's the lesson from Khoshin and Specker. So let me explain a little bit what all of this means. So we have to discuss what a hidden variable model is and when a hidden variable model is non-contextual. So HVM stands for hidden variable model, but that's a long word, and so I'm writing this down just once. Okay, what is a hidden variable model? So we have a bunch of observables. That's the first thing to talk about. And we call them A, B, C, and so forth. And so now we are testing the hypothesis that these observables here, they have values, maybe since the beginning of time. So they have values. And we call them lambda of A corresponding to A, lambda of B, lambda of C, and so forth. And now when a measurement happens, the idea is that these values are simply revealed when the measurement takes place. So, for example, like in classical mechanics, so if somebody measures my height, there's a certain outcome, meter and 83 or something like that, and I have this height before the measurement takes place, and when the measurement happens, that value is just revealed and nothing particular else happens. Of course, we know that quantum mechanics talks about measurement differently. And so the question is, can we set up a classical model like this and describe all the quantum phenomena with it? So this is the question. And Khoshin and Specker, like John Bell and others, figured out under certain additional assumptions, this is not the case. And here is the additional assumption that Khoshin and Specker used, and this is non-contextuality. So a hidden variable model can be non-contextual or contextual, and here we're looking only at the non-contextual case. And so let me write down what that is. Okay, so it's again about these observables and the corresponding values. So, for the observable A, the value lambda of A depends only on the observable A itself, and not the other observables that A might be jointly measured with. So again, the value that we assign to the observable A does not depend on all the other compatible observables that we might jointly measure together with A. This value only depends on the observable it belongs to. Okay? There's one more thing that I would like to say, and yeah, so what's hidden? Yeah, it's called hidden variable model. What's hidden here? Yeah? These values are not hidden. So what's hidden? So we all know that predictions of quantum mechanics are probabilistic, typically. So here, these values are deterministic. So how do we reproduce the probabilistic character of quantum measurement? So the way that we want to reproduce this is by having various values assignment, So we have lambda nu for all the observables from our set, yeah, going here as argument. So there's various ways to assign values to all these observables. So nu is from some set. So that set is the state space, the ontic state space of our hidden variable model. And now these ontic states nu, they can occur with certain probabilities, and then we are averaging the predictions of every value assignment over that probability distribution. So one could think that this is how the randomness of quantum measurement is reproduced in a hidden variable model. And that fails. That kind of talk does not work out, and the reason, the way this can be shown is by constructing sets of observables for which the value assignments, any possible value assignment, are contradicting. And Quotient and Specker did that in 1967 with a very complicated set of observables, and later these proofs were simplified. But at any rate, let me mention what the important result is here, and that's the Quotient-Specker theorem. Still a little bit of space. So this is the condition in Hilbert space dimension 3 or greater, non-contextual hidden variable models don't agree with quantum mechanics. And maybe it's worth pointing out, none of them agrees with quantum mechanics. So I want to review for you Mermin's proof of the Quotient-Specker theorem. I do not want to review the original proof because it's too complicated, but this one is really very simple. And it exists in two versions. There is the state-dependent and the state-independent version. Because of what we are going to discuss next, the connection with contextuality, let me talk about the state-dependent version. So here's where the state comes in. So we have a Greenberger-Horn-Zeilinger state associated with this arrangement of observables. And what do you note about the Greenberger-Horn-Zeilinger state? Maybe I give you a few seconds to think about. Okay, so the Greenberger-Horn-Zeilinger state is an eigenstate for all these four observables, which, by the way, means that these observables are all pairwise commutative. It's a very important property, and now, if you look at the other contexts, you see, oh, it works out on all of these lines, all the observables along it, they all commute pairwise. So now, these four observables have the Greenberger-Horn-Zeilinger state as their eigenstate. And so this means that these observables actually have values. And that's going to be our next question. So we wonder, can these 10 observables that you find here in this star, can they take values? That's the question. I should add one word here, consistently. So there will be constraints. So let's see what the constraints are and whether we can satisfy them. Okay, so yeah, let's begin with the simplest observables. Yeah, when we measure in the GHZ state, this observable will return eigenvalue 1. It's easily verified. And the other three will return eigenvalue -1. In each case, with certainty. So these observables do have values. So let's write that down. So the first has eigenvalue 1, first value is 1, the other three values are -1. Okay, so far so good, we are making progress. And now the question is, can these other observables shown here, can they have values too? Okay, so there's a few constraints that come from quantum mechanics. So our hidden variable model is supposed to reproduce quantum mechanics, and so those values cannot be arbitrary. Namely, what they need to be is eigenvalues of these observables. Yeah, these observables are Pauli observables, so there's only two eigenvalues here, +1, -1. So this means for all the other observables, but also holds for the ones we have already seen. So for all the observables, the values must be +or -1 to agree with the eigenvalues that these observables have. Okay, so that's the first constraint, first additional constraint beyond these. And then there's other constraints. So if you now look at these contexts, not only do the observables in each context, in each line, pairwise commute, but also they multiply to the identity, apart from this context where they multiply to minus the identity. Okay, but in the four remaining contexts, the four observables in them multiply to the identity. And so that also has an implication for the corresponding value. So our hidden variable model needs to reproduce this prediction, and this means that, for example, the value assignment for this observable times the assignment for this observable times the assignment for that observable must multiply to the assignment for that observable, which we actually know. So the three of them, this one times this one, they need to multiply to +1. So let's write that down. Okay, and we have similar relations for all the other contexts, the other three contexts that we haven't discussed yet. So next context, maybe this one over here. So the value of y3 times the value of x1 times the value of y2 needs to be the value of this, which is -1. And there's now two further such relations for the two remaining contexts. So which one did we not have yet? I think maybe this one we didn't have yet. So let's use this. So this is the constraints that we end up with. Okay, so now let's see if there's a solution to this set of equations. And we can easily show that there isn't. All we have to do is multiply these equations together. Then what do we get? On the right-hand side, obviously we get -1. And on the left-hand side, well, look at all the places. So for the first particle, we have the value of x1 twice and of y1 twice. But those values, as we have argued earlier, they must take values ±1. So this product is 1. You see the same over here. We have the value of x2 twice, here and here, and of y2 twice. So again, -1 plus 1 squared gives +1, so this is 1, 2. And the same happens in the third column. To summarize, these equations here are mutually contradicting. Namely, we have -1 equals +1, which obviously is a contradiction. So what does this mean? It means that we cannot even find a single consistent value assignment, not even a single one, and therefore the predictions of quantum mechanics cannot be reproduced by any non-contextual hidden variable model. Here shown for Hilbert space dimension 8 and above. This is how we make the proof simple, but the original proof applies in dimension 3 and higher. Okay, so this is what I wanted to say about contextuality of quantum mechanics. And in the next part, we will now be connecting it to measurement-based quantum computation.